Good morning, students. So the last two titles in this unit are simultaneous measurability of observables and uncertainty principle. So today we will discuss these two titles. The first one is simultaneous measurability of observables, and in fact we know already about observables. Observables are associated with the operators, but the title goes with the simultaneously measurement. So we have to measure two observables simultaneously, whether it is possible or not. Suppose we want to measure two observables and get the readings, those two observables are called compatible observables. So compatible observables, it says that we can measure two operators, two observables at the same time, and we'll get the answer. Okay, so this is what the compatible observable says. So mathematically it has to follow this commutator law. So commutator for any compatible observable is nothing but a comma b, which is equal to 0 with this bracket. Okay, commutator bracket with a comma b, which is equal to 0. Okay, this is called compatible observables. Answer doesn't exist, correct? There is no answer because this is equivalent to 0. So it implies that a and b can be measured simultaneously. We will get the answer. Okay, is it okay? Suppose if we get the answer, a comma b equals some answer. For example, if we take position operator, momentum operator. So in commutative bracket x comma p, which is equal to I h class, it implies that they are incompatible observables. They are incompatible observables. It means x and p cannot be measured simultaneously at the same time. Okay, because we get some answer. So x and p cannot be measured simultaneously. Okay, so they are all incompatible observables. So these two things are very, very important in the measurement of quantum systems in quantum mechanics. If two operators commute, so they are called commute, then both the quantities, both the observables, both the dynamical variables can be measured at the same time with infinite precision. But in quantum mechanics, it is not possible to measure two non-commuting observables. Okay, they are all called incompatible observables simultaneously to an arbitrary accuracy. So x and p. These x and p are dynamical variables. They are all in classical physics, they are called as canonically conjugate variables. So canonically conjugate variables, it implies that they are specified with some property. Okay, canonically conjugate variables. If two operators commute, so we can have the same set of eigenfunctions. If two operators commute, we can have same eigenfunction for both the operators. Okay, by definition, two operators a and b commute if the effect of applying a and b is the same as applying b on a. So ab equals b, and of course we know already a comma b equals ab minus ba, correct? We know already. So ab minus ba equals 0 means ab equals ba. That's all. So this condition should be satisfied for any commuting observables. So this condition should be satisfied. If two operators commute and consequently have the same set of eigenfunctions, so for two operators we will have the same eigenfunction. For example, a operates on psi, b also should operate on psi. So we can have, because a and b are commuting observables, so we can have two eigenfunctions of the same. Then the corresponding physical quantities can be evaluated or measured. So we can take the measurement of two observables at the same time if they are compatible observables with no limit on the uncertainty. In addition, in quantum mechanics, the configuration of a particle is fully defined by its wave function. Of course, we know already for any quantum system is described by a wave function. When a measurement of a particular observable, for example, position, angular momentum, energy, okay, and so on, is made on the particle, its wave function collapses. So if you want to measure one particle quantum system, it will collapse into another system. This transformation is nothing but linear transformation, which you have already discussed, and it collapses to eigenstates of the operator used to represent the observable whose corresponding eigenvalue gives the result of the measurement. So that value is nothing but eigenvalue. The following two theorems were very important related to simultaneous measurability of observables. The following two theorems indicate the connection between compatible observables and commuting operators. So they are all commuting operators as well compatible observables. Okay. First theorem: if A commutes with B, so A comma B equals 0. A commutes with B. They have a common eigenfunction. So we are going to prove that whether they have a common eigenfunction or not. As I said earlier, A acts on psi, B acts on psi, so they will have common eigenfunction. If A commutes with B, so for set of eigenfunctions, Ii goes from I equals 1 to 3. Okay, so A operator operates on psi A will give you eigenvalue with a eigenfunction. Okay, we know already. Similarly, B operator operates on eigenfunction will give you Bi psi A. We know already. Now I am going to multiply this by A. So AB psi A will give you A. B psi A is nothing but Bi psi A. So I can write Bi psi A. So I am going to multiply on both sides by A. Correct? And Bi is the value. So I can pull it out. So Bi, A operates on psi A. A operates on psi A will give you Ai psi A. So Ai psi A. So we will get the eigenvalue Ai Bi psi A. So AB psi A will give you the eigenvalue Ai Bi with psi A. So this equation is clear. Similarly, this equation, if you operate on B on both sides, okay, so B operates on both sides, that will give you B A psi equals B Ai psi A. And of course, A is the eigenvalue, it's a number, I can pull it out. So Ai B psi A. B psi A is nothing but Bi psi A. So I can write Bi psi A. You just look at these two equations, they are the same, right hand side. So right hands are the same, then left hand side must be equal, it must be same. So AB psi A equals BA psi A. AB psi A equals BA psi A, it implies that AB minus BA equals 0. So commutator A comma B equals 0. So it implies that A commutes with B. So this is what it's asked. Okay, it commutes with B. So compatible observables will commute. So theorem 1 is proved. Now we will go for theorem 2. Commuting operators will have a common set of eigenfunctions. Common set of eigenfunctions. So lot of eigenfunctions will be there. So common set of eigenfunctions, all two commuting operators. So we are going to prove this one. So A operator operating on eigenfunction will give you eigenvalue with eigenfunction like in this expression. Similarly, BA psi A will give you operating both sides from left by B. Okay, we know already this expression. You just operate B on both sides. So BA psi A will be BAI psi A. Correct? So we know already AB equals BA from theorem 1. So BA can be replaced with AB. So AB psi A equals BAI psi A. Okay. Now I am going to write this expression like this in this form. So A with a bracket B psi A equals AI, pull it out, eigenvalue with B psi A. So it implies that we get the eigenfunction, and this also is an eigenfunction. We can say. So it implies that B psi A is an eigenfunction of A with the same eigenvalue AI. With the same eigenvalue AI. Is it clear? So it implies that B psi A is the eigenfunction of A with the same eigenvalue AI. Okay, AI. So since B psi A equals Bi psi I, and B psi I, and you know B psi A can differ from psi I only by a multiplicative constant Bi. Okay, so this B psi I differs from psi I only by a multiplicative constant Bi, because B psi A equals Bi psi I. So it implies that psi A is a simultaneous eigenfunction of both A and B. Okay, so theorem 2 is proved. Now we will go for a small problem. Okay, consider a wave function of particle which is given by this psi of x comma t, psi wave function which depends on x and t, position and time, which is equal to e power I kx minus omega. It's a plane wave equation. Okay, it's a plane wave equation, e power I kx minus omega t. Now what is the question? There are three questions. Is the wave function is eigenfunction related to the dynamical variables or not? Okay, first point. Second one, does this represent the ground state? Ground state or excited state? And third one is, obtain the probability current density of this function. So 3 questions are asked. Okay. So first we are going to prove this one. Is the wave function is eigen function related to the dynamical variable? Okay. First we are going to prove. What are the dynamical variables from this expression? We can get e power ikx minus omega t. Okay. So we can have 2 dynamical variables. One is x. Another one is x. Okay. So dynamical variable x is there. Then another one is momentum p. We can get it from momentum p using this relation. And another one is the energy. Using this expression we can get. So they are all dynamical variables associated with the observables, associated with the operators. Okay. So p equals minus I h cross del. So just to differentiate with respect to x, that will give you momentum value. Okay, it's an observable. Is the wave function is eigen function related to the dynamical variables or not? Okay. So first observable we are going to find out. So now differentiate with respect to x. So just to differentiate with respect to x, that will give you ik e power ikx minus omega t. Okay. You are going to differentiate with respect to x. So minus, you have I into I square. So minus is there. So plus you will have h cross k e power ikx minus omega t. And of course h bar k is nothing but eigenvalue of the momentum. P equals h bar k. This is an eigenvalue of the momentum. So this is the eigenvalue of the momentum, and eigenfunctions exist. So it must be an observable. It must be a variable. Okay. The next one, energy. E equals I h cross partial d by dt. So we are going to differentiate with respect to time t. Okay. So now differentiate with respect to time t. That will give you I h cross minus I omega e power ikx minus omega t. Okay. So you have I squared minus 1. Already one minus is there. So plus it will go with plus. So h bar omega e power ikx minus omega t. Now again h bar omega is the eigenvalue of the energy. And eigenvalue of the energy E. So it must be also a variable. It's a dynamical variable. Okay, it's an observed. So the first question is very clear that P and E are dynamical variables. They are related with eigenfunctions. Okay. So given function is an eigenfunction. Second one, does this represent the ground state? So energy. So here we are getting only positive values. Eigenvalue and eigenenergy both are positive values. Okay. Energy of a bound state is always negative. Energy of a bound state. We always represent all the negative values for the bound state. If it is not unbound, if it is continuous, the energies will be positive. So energy of a bound state is negative. Here the energy eigenvalue is positive. So it is not a bound state. It is a free state. Okay. It is not a bound state. For all bound state, energies will be always negative. For example, for hydrogen atom, ground state, at the ground state, the hydrogen atom, the energy value is minus 13.6 electron volt. It is not plus 13.6 electron volt. So minus 13.6 electron volt. So it's a bound state. Okay, is it okay? Now the third one, obtain the probability current density of this function. So we know already the expression for current density is given by this. Already we learnt earlier. Okay, current density is given by this expression. Okay, psi del psi star minus psi star del psi. So this will be your assignment. Psi is given, correct? You have psi is given. You find out del psi, differentiate with respect to x, del psi. You just take the complex conjugate of the wave function and differentiate with respect to x. That will give you del psi star, del psi star. Okay, you multiply these two, and subtract these two expressions. You will get minus ik minus ik. So you will get minus ik. So you will get the answer h bar k by m. So probably you will get one minus sign. There must be a minus sign here. There must be a minus sign. Only then you will get h bar k by m. So there's a mistake here. So you will get one minus sign. There must be a minus sign here. There must be a minus sign here. Minus will give you plus. Correct. So it is not necessary. It's correct only. Wait. You will just pull minus I out. You just pull minus I out. That will give you I squared minus 1. So plus 1 So h bar k divided by m. So it's correct. So it's correct. Okay. You have h bar k divided by m. You will get 2ik. That 2 will get cancelled. So you will get h bar k by m. So this is the correct one. Okay. No problem. So any doubt in this problem? Come on. Any doubt? So now we'll go for uncertainty relation. So it's very important concept in quantum mechanics. Whenever we study a pair of observables means two observables. Okay, minimum two observables. If two observables exist, then we will have to use whether they are compatible or incompatible observables. First we will have to find out. Okay. So for example, x and p, just now we learned that they are incompatible observables. We cannot measure x and p simultaneously. Okay, so this is what we need. For compatible measurables we can measure, but in quantum mechanics 99%, we can say 100%, two observables always will be incompatible. Two operators we can't measure simultaneously. All operators will be incompatible observables, incompatible operators. So this was put forth by Heisenberg in the year 1927. So uncertainty principle was put forth. It was proposed by Heisenberg in the year 1927 when he was at the age of 26. Okay, so very young, 26. Now Heisenberg was born in the year 1901 in Wurzburg in Germany. So it's a small village. Heisenberg was born in a small village, and in fact in childhood he was very good at mathematics. So his teacher, his father was a teacher. He was a language teacher. He took some Greek language, then philosophy. Then they moved to Munich, that Munich city, and he got a job. His father got a job in university, and he became a professor there. And he took his family from the village to Munich. And in the early childhood, again Heisenberg, Werner Heisenberg, it's a full name. Werner Heisenberg started learning mathematics very well. So in fact, he would finish one mathematics book within a week or two. So his father used to bring some books from the library, from the university, and gave him a lot of books. So immediately you will say, after a week he will say that he has finished that book, this book and all. So that one book was inspired. That book name is Number Theory. So it was inspired by him. So number theory inspired him. So I can say that. So he took number theory and he started writing a research paper at the age of 16. But this paper was not published. So he was good at mathematics. He joined mathematics department in the university. And in fact, his teacher, who took mathematics, he said, "You know already maths very well. In fact, you are teaching mathematics to your senior students. They do even research work. And you are spoiling all our students. So better you just go and join some other course." So he said to his daddy, and the teacher also said to his father, and father decided that you know mathematics very well, so better you can join physics. In fact, Heisenberg did not like physics. He liked only mathematics very well. He used to solve all the problems through mathematics. So he joined, that's his father asked him to join under Sommerfeld. So Sommerfeld, you know already from German, he was a senior most scientist at the time. Sommerfeld, some corrections, we have already learned some corrections about atomic model, elliptical orbit. Okay, this Sommerfeld corrections we know already. So he joined under Sommerfeld. Sommerfeld, after looking at his talent in mathematics, he gave a problem, simple problem. At the time, Zeeman effect was very famous. Zeeman effect is very simple. It says that you have a spectral line. So when light interacts with an atom, we will get spectral lines. We know already. So this spectral line is subjected to a magnetic field. Suppose if we consider a spectral line, and when it is in the magnetic influence of the magnetic field, then this line will split into three lines. For example, I have a spectral line. This is a spectral line. We consider this is 1000 angstrom. If it is a powerful magnetic field is there, and this line will split into 1001 angstrom and 999 angstrom. So 3 lines it flit. So at the time that Zeeman effect was very famous. So Sommerfeld asked Heisenberg, come on, you are good at mathematics, you just draw the theoretical model for Zeeman effect. At the time that quantum mechanics was just evolving. Okay, the de Broglie hypothesis, Schrödinger's idea of wave function, Albert Einstein's idea of dual character, Max-Planck's theory. So he started studying all the elementary quantum mechanics, and he derived within a week. He derived the Zeeman effect theoretically within a week. His professor, that is Sommerfeld, he asked him, come on, you can submit your PhD on Zeeman effect. He said, no sir, I want to find out a new idea, new one. This is already, it has been found by someone else, Zeeman. But I want to find new in physics or mathematics. Then I'll get my PhD. So this is what he said. So at the same time, in the year 1922, Niels Bohr, he got a Nobel Prize. So he shared his Nobel Prize along with Albert Einstein. Albert Einstein got Nobel Prize 1921 for Nobel Prize in the year 1922. So 1922, two persons got Nobel Prize. Two famous persons got Nobel Prize. So Albert Einstein and Niels Bohr. Niels Bohr for atom, Albert Einstein for photoelectric effect. So one is for light, another one is for matter. So light interaction with matter. See, very light interaction with matter. So Niels Bohr from Denmark, he came to Germany, Göttingen, the place, and he gave series of lectures. So every evening there is a series of lectures. And Sommerfeld and Heisenberg, both they attended this lecture. Okay, so there was a seminar. So in the year 1922, at the time his age was 21, correct? Niels Bohr, Heisenberg's age was 21, correct? And while giving lectures, Heisenberg asked many questions. He was so young, he asked many questions. Even the audience surprised. What this small guy is asking a lot of questions. Then at the end of lectures, Niels Bohr and Heisenberg, they came together and they discussed a lot of things while going for hiking in the mountain, trekking in the mountain. They discussed many things. At the end, Niels Bohr said, you are so intelligent and you are able to answer all the questions whatever I propose. After a year, there was a chance to go to his place. That is, Heisenberg went to his place, Denmark. Heisenberg was from Germany, okay, Göttingen, and he went to now his place, that is Niels Bohr's place, Denmark. Denmark, where in which Copenhagen, that's a place where Niels Bohr, he built a research work. Niels Bohr was very, very rich. So he had his own research place. He used to invite all the other scientists and used to discuss with them. So Heisenberg went to his place and they started discussing about atoms, about the light and all those things. They used to discuss right from the morning. They will have breakfast. They will discuss. They will go outside to the bar, to the tea shop. Again they will come back. They will discuss again. At the night, up to the night they will discuss. So when they discuss, even at the bar or even at the tea shops or the outside, and there will be a lot of discussion on quantum mechanics. The owners of the bar, owners of the tea shops, sometimes they said that don't talk quantum mechanics in the shop. So they used to write here in the shop. So we usually will hear that don't talk politics here. Correct? In the tea shops, we have seen don't talk politics here. But they used to print out that don't talk quantum mechanics here. So there was a lot of discussion they used to discuss. You know, Niels Bohr was an experimentalist and Heisenberg was a theoretician. So he had a lot of data. Niels Bohr had a lot of data. And at the time he was so interested in mathematics, especially in matrix. So he wanted to solve some eigenvalues through square matrix. And he took the data from Niels Bohr's idea and he started finding out the eigenvalues. These eigenvalues which he obtained exactly matches with the experimental results. So that was the inspired part. So inspiration. So exactly after some time, after a year, 1925, he proposed matrix mechanics. So in the year 1925, he proposed matrix mechanics, very famous for his matrix mechanics. So 1926, Schrödinger proposed wave mechanics, and both were equivalent. It was proposed by again Schrödinger. So 1927, next year. So 1932, he got the Nobel Prize for proposing this matrix mechanics, not for uncertainty principle. Okay, of course, uncertainty principle is very famous, we know already. But above all, the matrix mechanics is very important. And the Nobel Committee decided to give the 1932 Nobel Prize for Werner Heisenberg, for the discovery of quantum mechanics. So matrix mechanics is for the discovery of quantum mechanics. This is one of the avenues of attack. One avenue of attack is wave mechanics. Another avenue of attack is matrix mechanics. Put together, it's a quantum mechanics. So one is an abstract method. Another one is using wave functions. We can derive Schrödinger wave equation. So 1932's Nobel Prize he got in the year 1933. So in the year 1933, 3 persons got Nobel Prize. Okay, one is Werner Heisenberg, and one is Schrödinger, then last person was Dirac, Paul Dirac. So 3 persons got Nobel Prize. Okay, so actually matrix mechanics was proposed and discussed by two of his friends, with 2 of his friends. So Heisenberg, Jordan and Max Born. Put together only they proposed, but however Heisenberg he put forth all the ideas, so he got the Nobel Prize. Max Born got the Nobel Prize later in the year 1954 or some other thing, and Jordan did not get the Nobel Prize. So that's the story. Okay.